Hello everyone, this is lesson 1. We will talk today about Lagrange interpolation, and we need Lagrange interpolation for differentiation and integration, but also we can use it to evaluate a function if we have some points and we need to find a value of our function somewhere between these points. And also in interpolation there also exists extrapolation, which is kind of different, and extrapolation is used when we want to find a value of our function outside of the range of given points. And let me show what I mean. For example, we have
some x, which is our data, and f of x
is our value of function which we want to estimate. And for example, we have some points. And interpolation means that we are looking for the value, for example, somewhere here at some x1. And for example, we can use linear interpolation. We first find the curve which passes through our points. It's a bad interpolation, don't care. And we say that the value of our function at x1 is equal to f at x1. And extrapolation is when we want to find a value outside of the range of our points, and the range of our points is actually lies between the most left point, let it call x left, and the most right point, extra. Here is interpolation. And extrapolation. And today we're not going to talk about extrapolation, and actually if you want to do extrapolation, go to machine learning courses. They will give you a comprehensive guide how to do it. And we will focus on interpolation. And in interpolation there exist two kinds of interpolation. First is where we fit exactly our interpolated function into our points, and the second one is when we are looking for the least square error. Is when we want to find, for example, a curve which minimize the square distance between our actual points and our predicted points. And in our numerical methods, we will talk about only when we fit our value exact, because we need it for differentiation and integration. So let's move to Lagrange interpolation. It's a basic one for finding a value between the points. And idea is simple. We have some data. Let it be x0, xn. We have the values. F of x0, f of xn. And we want to find how to get these values out of these data points. And for this, we will use a basis, and let's call our basis phi. And idea is that we want to say that f of xi is equal to the sum of some coefficients j times fj of xi, and we sum over j from 0 to n. So idea is we are looking for such basis so that we can decompose our value f of xi in this basis with some coefficients aj. And now we want to find the best basis for our decomposition so that we can easily first find this decomposition and then use this decomposition. And let's rewrite our interpolation a little bit in a different form. And here we will use a matrix representation, which will be helpful if you want to implement it numerically. And later we will use a lot matrix representation. So started with matrix representation.
We have our coefficients, and it's equal to, here's our matrix consisting of our basis at data points, our matrix, and here are our coefficients, A0, AN. And
we assume that coefficients are constant for any data. We want to fix our coefficients, find the matrix so that we have, and the idea is that first we actually want to find the basis, and if we know the basis, we can then find our coefficients and use them later for interpolation of any value between our data points. And here you can see that to find our coefficient A0, AN, actually we need from our matrix that it would be easily to invert, because our coefficients, which we are looking, actually, we don't know them.
actually equal to the reverse matrix of our basis at our data points times the vector of our values.
And therefore, what we need from our interpolation easily invertible matrix. But also, since we want to use this technique for differentiation and integration, we also want that our basis functions, they are simple. And what is the most simple function? It's polynomials. And we want
Simple. And differentiation, therefore, polynomials.
because we know how to differentiate and integrate polynomials, it's trivial.
And now
The first idea to use as a basis function just x to the power n. And let's write it first idea. Phi I of x is actually just x to the power I. And then when we want to say that our f of xj will be equal to ai times xi. And here we will get the problem that our matrix is not easily invertible, it will be dense. And what we want, we actually want some diagonal matrix which we know how to invert easily. And to do that, what we want from our polynomial, it's xj. Xj. What we want that at points xj, all of the values is equal to 0, and only phi j is equal to non-zero value. To get easily invertible matrix, we want diagonal matrix. And diagonal matrix means that phi I at point xj, and it will be 0 if I is not equal to j, and it's convenient to set it to 1 and then just use this coefficient to make value of function at point xj just equal to f at xj if I is equal to j. And now our problem is reduced to finding such functions f of x, so such that at the index I at point j it's equal to 0, and if I equal to j it's equal to 1. And how to do that? It's just we use a theorem from algebra that if we have a roots at xj, then we can decompose it into xj values. And our first idea is say that f of phi I from x is equal to x minus x1,
x minus x2, and so on, x minus xn.
and here it doesn't contain x minus xi. And let's rewrite it a little bit differently. To simplify our notation, we'll say that it's equal to the product of j from 1 to n, j is not equal to I of x minus xj. And let's check that at point xj, where j is not equal to I, we get 0, it's trivial. And now only what we left is to normalize our function so that at point xj we have 1. And to do that, let's see what we have at point xi of our function phi I. It will be equal to the product from j equal to 1, j is not equal to I, of xi minus xj. And we
Can I do that? Yeah.
and we want that value equal to 1. Well, and here we can have some, for example, coefficient alpha. And from here it follows that alpha is actually equal to 1 over product of j from 1 to n, j is not equal to I, of xi minus xj. Therefore, our function phi I will be equal to the product from j equal to 1, j is not equal to I, to n x minus xj, divided to the product of j equal to 1, j is not equal to I, n xi minus xj. And let's call this function Li from Lagrange interpolation. And now we say that our Lagrange interpolation is actually our f of x is equal to the sum of f, our function f of x is equal to the sum of our function f at our given data, f of xi, times our basis Li at point x. And let's check that at our given data we have exactly f of xi, for example, and check for x equal to xj. What we get? We get sum of f xi, Li xj, I is from 1 to 0. And we know that our Lagrange function will be equal exactly to 1 only at point I equal to j. And it will be equal to f of xj. So, as we want to. And this is a Lagrange interpolation. Let's review what we have discussed. Lagrange interpolation starts as the following. We have our data and we have our values. We want to find such representation of our function which fits our values and data. And we are looking for the function, let's call it f of x, which will be equal at our data points, our values, to find some value in between our data points. And here we used first the idea of matrix representation. We know our values, and we assume that we know our matrix. We want to find our coefficients to decompose our values. And to find easily our coefficients, we need a good matrix. And good matrix is one which easily invertible. And in our case, we can consider a diagonal because we can easily invert diagonal. Just take the inverse of every element. And also, we want further from our interpolation to simply integrate and differentiate our function. Therefore, it's convenient to use polynomials. And our first idea was to just take power series. For example, we say that our basis phi I is equal to x to the power I. However, this representation has some problems because the matrix is dense. And next, our idea was that, okay, let's use polynomials, but we will fix them a little bit. And by fixing, I mean that we want that our values, our matrix is diagonal. And how to get diagonal matrix? We first set the problem. We are looking for the function phi I such that at point xj it's equal to 0 if I is not equal to j, and at point I equal to j it's equal to 1. And we can find this representation by using a theorem from the algebra that we can decompose our function into the roots. And next we use a second condition that we want to have 1 at point j, at I equal to j. And we find our Lagrange Interpolant, Lagrange basis. And then we say that our function f of x, which is interpolation of our data and values, will be equal to the sum of our values at points xi times our Lagrange basis at point I. And we checked that for any point xj, which is our data, our interpolated function is equal to our given function. So therefore, our interpolant passes through all given points, and we are done. And let's consider example. Exponent. Assume I want to interpolate exponent. And to interpolate exponent, let's assume that we also set n equal to 2, just to simplify our calculations. And let's take the first point is 0, and since we are counting from the, here it was a little bit confusing because somewhere I used indexing from the 0, but then I moved to the indexing from the 1, and don't be confused, please. I found small misprint, let's say it like that, because here I used indexation from 0, but then I moved to indexation from 1. And to have our formulas consistent, let's change everywhere our notions that we start with 0. Oops. Yes, and let's consider our example. We want to consider function exponents, and we have n equal to 2. That means that we have 3 values, and let it be 0, 0.5, and 1. We are looking at our function f of x. Let's calculate f of xi. It's equal to 1. This one I cannot calculate, unfortunately, and f of x2 is equal to e. And now let's fit our interpolant.
This will be equal to 1 times x minus x1, x minus x2 divided by plus 0.5 x minus x0, x minus x2, x1 minus x0, x1 minus x2 plus e to the x minus x0, x minus x1, x2 minus x0, x2 minus x1.
And if you check, this is actually quite good approximation of our exponent in a range from 0 to 1. And for x is equal to 0.25, we get that our f of x will be equal to 1.26, and the actual value is 1.28, and here is the 4. So we get pretty close approximation of our function. That's all for Lagrange interpolation. Next we will consider Hermite interpolation, and then we will move to some more interesting topics in interpolation. Thank you for watching, and keep rolling.